The temperature is 47 degrees Celsius. The sun is directly overhead, and the ground surface is radiating heat at something closer to 70. There is no shade for 2 kilometers in any direction. You have no water bottle, no sunscreen, no synthetic fabric engineered to wick moisture away from the skin, no vehicle, no building, no infrastructure of any kind between you and the full thermal output of a star at 93 million miles distance, concentrated on a pale primate with no fur standing in the middle of an open landscape. By any reasonable calculation, you should be dead or dying within 2 hours. Core temperature above 40 degrees Celsius causes proteins to denature. Above 41.5, the brain begins to fail. Above 42, multi-organ shutdown begins. And yet the fossil record shows that Homo erectus was ranging across the open savanna of East Africa in conditions like this over 1 million years ago. The sand people of the Kalahari have been running prey animals to exhaustion across open desert in midday heat for thousands of years. The Aboriginal Australians crossed and inhabited some of the hottest landscapes on Earth without technological cooling of any kind. They did not merely survive extreme heat. They moved through it, worked in it, and thrived in it. The question is how? Because the answer is not willpower. It is one of the most sophisticated biological and behavioral systems in the history of mammalian evolution, and most of it is still running inside you right now, largely unrecognized. The answer isn't one thing. There are layers here in eccrine sweat glands, in bipedal geometry, in the behavioral protocols of the San and the Anbara, and in what happens to a body that is deprived of heat stress entirely. Each layer changes what you thought you knew about human limits. Let's go. Start with the biology, because before any behavior, before any cultural practice, the human body itself is one of the most extraordinary heat management systems in the mammalian world. And it was built specifically for open, hot, exposed environments. Peter Wheeler at Liverpool John Moores University published a series of influential papers through the 1990s modeling the thermal advantages of bipedalism in equatorial heat. His calculations showed that an upright bipedal body in midday equatorial sun presents roughly 60% less surface area to direct overhead radiation than a quadrupedal body of equivalent mass. Standing upright also raises the body's center of mass away from the superheated ground surface, where air temperature can be 10 to 15 degrees higher than at head height due to convective heating from the ground. A bipedal hominin standing in open savanna at midday is simultaneously reducing its radiation load, accessing cooler air, and positioning itself to catch convective breezes that do not reach ground level. Bipedalism, usually discussed as a locomotion adaptation, was also a heat management adaptation. The shape of the human body in the landscape is a thermal solution. Here's where it gets strange: the sweat. Humans have between 2 and 4 million eccrine sweat glands distributed across the entire body surface, far more than any other primate and more than almost any other mammal. A chimpanzee, under heat stress, cannot sweat efficiently enough to sustain prolonged activity in direct midday sun. Its primary thermoregulation strategy is behavioral avoidance, moving into shade, reducing activity, waiting out the heat. A human, at peak sweat output, can produce up to 1.5 liters of sweat per hour, and because human skin is largely bare, that sweat evaporates directly from the surface into the surrounding air rather than being trapped by dense fur. The evaporative cooling capacity of this system is extraordinary. Evaporation of 1 liter of sweat removes approximately 580 kilocalories of heat from the body, roughly the equivalent of the heat generated by an hour of moderate running. Dennis Bramble at the University of Utah and Daniel Lieberman at Harvard, in their landmark 2004 Nature paper on the evolution of human endurance running, argued that this sweating capacity was not just a survival mechanism but an active predatory tool. The persistence hunt running prey animals to exhaustion across open ground in midday heat works because the human sweating system can sustain thermoregulation across 2 to 4 hours of continuous exertion in conditions that cause fatal hyperthermia in the quadrupedal prey within that same time window. The animal stops to pant in the shade. The human keeps running. Heat was not a threat to be survived. It was a weapon. Now, let's talk about what ancient behavioral heat management actually looked like, because the biology is only half the picture. The behavioral protocols that traditional cultures developed for living in extreme heat are documented in enough ethnographic detail to reconstruct their logic precisely. Rosalind Haynes, at the University of New South Wales, studying the thermal practices of Aboriginal Australian desert groups, documented a suite of behaviors that together constitute a comprehensive heat management protocol. Activity scheduling is the first layer. In extreme heat conditions, the Anbara people of Arnhem Land traditionally compressed physically demanding work into the early morning hours from roughly 4 a.m. to 9 a.m., and again in the late afternoon from 4 p.m. to 7 p.m., with the central hours of the day reserved for minimal exertion activities in shade. This is not laziness. It is chronobiology applied to thermal management, exploiting the body's lower core temperature in the early morning, when less sweating is required to maintain thermoregulation for the work that demands the most physical output. The hottest hours are reserved for skills that require attention rather than exertion. Tool making, storytelling, social activity, instruction of the young. The day is thermally segmented. Every segment is used. Nothing is wasted. But the sequencing is precise. Here's something else that almost never comes up: the water knowledge. Surviving extreme heat without technological water storage requires a specific and extensive understanding of the landscape's hidden hydrology and the traditional ecological knowledge systems of desert-dwelling cultures. Encode this understanding at a depth that consistently astonishes researchers encountering it for the first time. David Trigger at the University of Queensland, studying Wanyi and Garawa knowledge systems in northwestern Queensland, documented that senior knowledge holders could identify subsurface water sources, soakages, rock holes, water-bearing root systems of specific plant species with accuracy that hydrological survey later confirmed, across territories spanning hundreds of square kilometers. The Spinifex hopping mouse, Notomys alexis, was observed by Aboriginal trackers as an indicator of shallow subsurface water. The mouse cannot survive more than a day's travel from water and its runways. Read by experienced trackers, provided directional information about water availability in terrain that appeared uniformly dry to European observers. The bloodwood tree, Corymbia terminalis, was known to indicate water within a specific depth range when its roots were examined. Certain rock formations were known to collect water in internal fissures after rain and retain it for weeks after the surface had dried completely. This is not folklore. It is a precision ecological database accumulated across thousands of years of survival in an environment that kills the uninformed within days. So here's the part nobody tells you. The human body is not adapted to tolerate heat passively. It is adapted to manage heat actively, and the management requires practice, acclimatization, and specific physiological changes that only occur under repeated heat exposure. Heat acclimatization, studied extensively by exercise physiologists, including the research group of William Kenny at Pennsylvania State University, involves a suite of measurable physiological adaptations that develop over 10 to 14 days of regular heat exposure. Plasma volume expands by up to 20%, increasing cardiovascular heat transport capacity. Sweat onset temperature drops, meaning sweating begins earlier and prevents core temperature from rising as high before cooling commences. Sweat rate increases for equivalent workloads. Electrolyte concentration in sweat decreases, reducing salt loss per liter of sweat. These are not trivial changes. A heat-acclimatized body has a fundamentally different thermal capacity than an unacclimatized one. It can sustain higher exertion levels at higher temperatures with lower cardiovascular strain. Ancient humans living in hot environments year-round were continuously, chronically acclimatized. Their physiology was running at peak heat management capacity every day. A modern person who spends most of their life in air-conditioned environments is, by this measure, thermally unfit for the conditions their own body was designed to handle. The capacity is still there. The acclimatization is not. There's one last thing I saved for the end: the Kalahari persistence hunt. Documented in detail by Louis Liebenberg, a South African scientist who spent years running with sand hunters in the Kalahari and published his findings in the Journal of Human Evolution in 2006. The persistence hunt is one of the most clarifying demonstrations of ancient heat management in practice. Sand hunters track a kudu or gemsbok in midday heat, specifically midday, specifically the hottest hours, specifically the conditions that most disadvantage the prey, jogging at a pace that keeps the animal moving faster than its trot, preventing it from settling into a sustainable gait, raising its core temperature across 2 to 4 hours until it is unable to continue. The hunters are not faster than the kudu, they are cooler. They are sweating efficiently, tracking the animal's thermoregulatory state from its gait and breathing, reading the landscape for shade the animal might retreat to, cutting off those retreats. They are managing a heat differential across a landscape, using their own thermoregulatory superiority as the hunting tool. Liebenberg ran these hunts himself, as a moderately fit adult male with no special preparation, and completed them. The capacity is not lost. It is available in the same body, under the same sun. What the sand hunters have that most modern humans lack is not better biology. It is continuous acclimatization, precise behavioral scheduling, deep landscape knowledge, and the specific skill of reading another animal's thermal state from its movement. It is knowledge accumulated across thousands of years of living in heat without the option of leaving it. The temperature is 47 degrees, and the sun is overhead and you are standing in the open. Your 2 to 4 million sweat glands are active. Your upright posture is reducing your radiation load and lifting you into cooler air. Your plasma volume, if you have been acclimatizing properly, has expanded to move heat to the surface faster. You know where the water is. You know which hours are for running and which are for stillness. You know the specific hollow in the rock formation 3 kilometers northeast where water collected after the last rain and has not yet evaporated. You are not surviving this heat. You are using it. The human body in extreme heat, fully acclimatized, behaviorally calibrated, and equipped with the right landscape knowledge, is not at risk. It is at home. The heat was never the enemy. Ignorance of how to live in it was. And that ignorance is, of all the things ancient humans managed to avoid, the one we have most successfully cultivated.